In the last video, we looked at the idea of ionization energy, which concerns the energy change when we take an electron out of an atom. In this video, we're going to focus on the flip side of ionization energy, which is electron affinity, and it concerns the energy change when we drop an electron into an atom. So let's get started looking at this concept. Our formal objectives are the following. We'd like to be able to define the term electron affinity and give the relevant equation. We'd like to be able to identify and explain the trends in EA down a group and across a period. And finally, we'd like to be able to differentiate between electron affinity and ionization energy. So let's get started by trying to arrive at a definition of electron affinity. To do this, we're going to start by reconsidering ionization energy, which we looked at in the last video, so that we can properly draw the parallels between these two concepts. With ionization energy, we told the following story. Say you have a neutral atom. If you add a certain amount of energy to it, you can liberate the outermost electron from that atom, and the minimum energy required to liberate that outermost electron we call the first ionization energy. And we said that ionization energy, generally, you can think of it as analogous to the amount of energy required to liberate a spaceship, a space rocket, from the gravitational pull of our planet. And so we arrived at this definition of first ionization energy, which is the minimum energy needed to remove the first electron from a neutral gaseous atom. And how do we define first? We define first by referencing the most loosely held electron, which in this case here will be the outermost electron. We could also give a more general definition of ionization energy as simply just the energy needed to remove an electron from a gaseous atom or ion. So notice here it could be an ion, whereas here it must be a neutral gaseous atom. Now the equation for this, the formal equation would be this. So you take a neutral lithium gaseous atom, and it becomes a lithium cation plus a free electron. And the associated energy change there, delta H, if you've done thermochemistry, or you could just do IE for ionization energy, is 520 kilojoules per mole. Let's look now at electron affinity and see what are the parallels. With electron affinity, we again start with a neutral atom, in this case, for the first electron affinity. And what we're going to do instead of taking away an electron is we drop an electron into this atom. And when we drop an electron into the atom, we're going to release a certain amount of energy, which we call the electron affinity. And here we have created an anion, right? Because it has 3 protons and 4 electrons, so 1 more electron than it has protons. And the analogy for this is, you can think, when a spaceship or a space rocket is returning to the planet. So it's going from a freely floating body, and now it's falling back down into our planet. And if you've watched enough space movies, then you know that as they come back in, they heat up, releasing all that heat and light. And so that heat and light there is analogous to the electron affinity. So notice here that the electron affinity is actually an energy value. It's an energy change, right? The word sounds, or the phrase sounds like it's kind of like how much is the atom pulling, but it doesn't describe the amount of pull. It describes an energy change, although it is related to the amount of pull. So here is the formal definition of the first electron affinity. It is the energy change when an electron is added to a neutral gaseous atom, like this guy here. This is the first electron affinity. Or we could just give a general definition of electron affinity as the energy change when an electron is added to a gaseous atom or ion. So if we wanted to take this guy, which is already an anion, and add another electron to it, then the energy change associated with that would be the second electron affinity. Okay? And so we can give either the definition for the first EA or a general definition for EA. Now, what is the formal equation for EA, for electron affinity? Here we have a lithium gaseous atom gaining an electron to form a lithium gaseous anion. And the associated energy change here is the electron affinity. You can write it as delta H, which is the change in enthalpy if you've done thermochemistry. And the associated change there is minus 59.6 kilojoules per mole. That means 59.6 kilojoules are given out for every mole of electrons that fall into a mole of lithium atoms. Now, an interesting question you might have is, why is there a negative sign here, right, when here we had a positive sign? Why is this negative? Well, we can think of the lithium atom and its electron, or that electron that got dropped in, as a system. And in the before of the system, we had this free electron that had a certain amount of potential energy. And as it falls in, it's basically emitting that energy, kind of like that, as heat or light, and that energy is leaving the system. So by the time it has fallen into the shell, this system has less energy in the after state than it had in the before state. And because we have an energy drop, or an energy sort of release out into the surroundings, we say we have lost energy, and therefore the sign there should be negative. We have a negative energy change. Okay, so we lose energy from the system, and therefore the change is negative. Now let's compare the electron affinity of lithium to the electron affinity of another element, in this case here, fluorine. So we're going to drop an electron into fluorine's outermost shell there and release a certain amount of energy, which is the electron affinity for fluorine. Now, what is that value? We can see here it's minus 328 kilojoules per mole. So it's a lot more energy released here than is released here. How do we talk about the differences between the energies released here? You might be tempted to say that fluorine's electron affinity is higher than lithium's electron affinity, because this number, the absolute value, is bigger. But then because this is negative, in some sense, it is actually lower than that one. And so what I recommend is you don't even use the adjectives higher or lower when talking about electron affinity. Rather, you should be partial to the terms more and less exothermic. Exothermic, exo means to leave, right? It means outside, and thermic means heat. So exothermic means a loss of heat. So here we lost more heat from the system than here, or we lost more energy in this case than here. So we would say that fluorine has a more exothermic electron affinity than does lithium. And an important fact, which we'll come back to, is that highly exothermic electron affinities generally correlate with high reactivity for the non-metals. That was a fairly dense slide. Let's look now at some questions. I say we are about an orange light with this first objective, to be able to define the term electron affinity. Although we can do more than define it now, we can really explain it, right? And we should have the relevant equation in mind. Let's answer some questions based on that. Here's the first one. Which of the following equations corresponds to the first electron affinity for fluorine? As always, pause the video and read through the options. In 2 seconds, I will show you a clue, 1 and a 2, and a clue. In 2 seconds, I show you the answer. Pause if you want to read through the clue and inform your answers. 1 and a 2 and an answer. The answer is D. So let's see if we can cross out the others. So this one, A, we start with a singly negative fluorine gaseous anion, and we gain an electron to form a doubly negative fluorine gaseous anion. This is a kind of electron affinity, but it's the second because we started with an ion. Okay, so because this is the second EA, then it's wrong. In this case, what's happening? We're losing an electron to form a cation. So this would actually be ionization energy. So this is wrong as well. Okay, this one, what's happening? We're gaining an electron to form a singly negative anion. So this is the first electron affinity, except the fact that we've defined it here for solids. And we know that electron affinity and ionization energy are defined for the gaseous state. So this is also wrong, leaving us with that last correct answer. Let's look at another question. Which of the following is incorrect about the first electron affinity? Again, pause the video, read through the options, think about how you would answer it. In 2 seconds, I show you a clue, 1 and a 2 and a clue. In 2 seconds, I reveal the answer, 1 and a 2 and an answer. So the answer is D here. It is not called the first ionization energy. The first ionization energy is kind of the opposite of electron affinity. Let's quickly confirm that the other three are indeed true. It is usually exothermic. We said that is the case, right? Because energy is lost from the system when an electron falls into the atom, right? That's usually for the first electron affinity. That would be the case. Secondly, for nonmetals, a highly exothermic electron affinity corresponds to a high reactivity. This we said at the beginning of the first slide. I haven't really explained it yet. We'll do that in an upcoming slide. Finally, we had said that for an element, the relevant equation, if we just take any random element, call it X, the equation is a gaseous neutral atom gains an electron to form a singly positive anion. I've been using the terms anion and cation. Hopefully you know what those are, and you remember how to remember what they mean. Remember how to remember. So N here you can think stands for negative, so this is a negatively charged ion. And the T here looks like a plus, so this is a positively charged ion. So now we have a green light with this first objective to be able to define the term first electron affinity and give its equation. Let's look now at being able to identify the relevant trends. So here we have the first 20 elements of the periodic table, and at the top right I have put in kilojoules per mole the first electron affinities of each of these elements. You notice that some of them are above 0. That basically means that it's non-applicable for them, right? Because we had said that when an electron falls into an atom, it generally releases energy. If it requires energy to fall in, then usually it's not going to fall in. So generally, if it's above 0, we just consider it as not applicable, and I put above 0 there. But see if you can observe some general trends if you ignore the ones that are above 0. So pause the video if you like. Here's the first trend, is that across a period, it tends to get more exothermic. So we start with lithium here at minus 60 kilojoules per mole, and we end up there with fluorine at minus 328. Or over here, we start at minus 53, and we end up there at minus 349 kilojoules per mole. So it's getting more exothermic. So for example, for chlorine, this means that we would release 349 kilojoules for every mole of electrons that we drop into a mole of chlorine atoms. Now, how about the trend down a group? It seems that there is a reduction in the exothermicity as we go down the group. So here, this is the most exothermic in this group and the least exothermic in that group. How do we explain these trends? Let's start with the period trend. It's the same way we explained all the other trends, really. Nuclear charge and atomic radius. Let's look across a period. We say that across a period, the nuclear charge increases, and this pulls the electron cloud closer. So here we start with a nuclear charge of 3. The 3 I've written in this nucleus means that there are 3 protons in there, and we go over there to 9 protons. And so the pull on those electron clouds is increasing because the number of protons in the nucleus is increasing. And because of that fact then, when a new electron is brought into the shell, it's brought into a position closer to the nucleus. So it's kind of like a bigger fall, right? So because it's coming in closer to the nucleus here, the pull is stronger, and the fall, the energy released when it falls is larger. Let's look at an analogy to try and understand what I'm saying there. So we take lithium and we take fluorine, and we imagine the energy change associated with an electron dropping into each atom as the following analogy. So we meet this guy, Electric Mike, that does crazy stunts like jumping from buildings onto mattresses. So here he is for lithium, and there for fluorine. Now, for lithium, we can think of the shells as looking like this. And for fluorine, we can think of them as looking like that. Why do they look like that? Well, lithium has 3 protons and 2 shells, right? So 3 protons and 2 shells. But because it only has 3 protons, the protons are not able to really compress these shells. So the shells are kind of diffuse here. Whereas over there, the 9 protons are able to fully compress those shells. And so you have kind of a slimmer cushioning. So when an electron falls into, say, lithium, it receives a lot of cushioning, and therefore the energy release, you can think how loud a sound it's going to make, is not going to be very, very large. The energy release here will be fairly small relative to the energy release there. Okay, and that's why the electron affinity for lithium is just minus 60 kilojoules per mole, whereas for fluorine, it's minus 330 kilojoules per mole. So that is the idea for the trend across the period. You have the same number of shells, but the shells are less diffuse. The atomic radius is smaller, and so the electron comes into a position closer to the nucleus. Let's look now at the trend down a period and how to explain it. Sorry, down a group, I mean. So we had said that it gets less exothermic down a group. Here's the reasoning. New shells are added as we go down a group, and these shells are going to what? Take up space due to repulsion from shells below. So as we add new shells here, 1 shell, 2 shells, 3 shells, and 4 shells, you can see that the outermost shell is basically kind of nice and diffuse because of repulsion from the shells underneath, right? And because of that fact, when a new electron is brought into a position, it comes in generally further to the nucleus. So new electrons will be brought into positions further from the nucleus. So if we brought in, what's going on with my pen? I turned it off. If we brought in an electron, let me get my pen back. If we brought in an electron here into potassium, it would fall basically very far from the nucleus, whereas here for hydrogen, it falls in very close to the nucleus. And therefore, the electron affinity here is more exothermic than it is over there. Let's look at an analogy for these, considering lithium and potassium. So here we have lithium and we have potassium, and we notice that here the electron affinity is more exothermic than it is over there. We bring back our stuntman, Electric Mike, and again he's jumping into the atom, right? And what's pulling him is not gravity, but rather the electrostatic pull of the nuclei, of the protons in these nuclei. And there's a certain amount of cushioning in each case. For lithium, we have what? 2 matrices, 2 shells. But for potassium, we have 4 shells. So even though potassium has a higher nuclear charge and the lower shells are kind of more constricted, because we have more shells, it more than compensates. So when Electric Mike, or the free electron, jumps into the shell of potassium, it's a shorter fall and therefore less exothermic than when he jumps into the shells for lithium. So this is more exothermic, and that is what? Less exothermic. Hopefully that analogy is not too stupid and it gives you the right idea. So now let's look at the full periodic table and the general trends. As you can see, it's not as clean a trend as you would like, but we can notice the general idea. So we notice that it gets more exothermic across a period. So for example, for the halogens, it's highly exothermic. We release something like 300 kilojoules for every mole of electrons there. Whereas over here, as the alkaline metals and the alkaline earth metals, it's very close to 0, so you release barely any energy when electrons fall into those atoms. So it's fairly clear that there's a period trend. The group trend is very slight. So we notice that, for example, if an electron falls into hydrogen, there's more energy released than an electron falling into, what is that, francium over there, right? So it gets less exothermic down group 1, at least. And it also seems to get less exothermic down group 17, right? So for example, fluorine and chlorine have highly exothermic electron affinities relative to the ones further down, acetine and so on. Okay, so now we have a general sense of the trend. These data are in your data booklet. So at the top right of section 8, each cell in section 8 has the first electron affinity in kilojoules per mole for each element. Some of them are missing, and also some of them have the second electron affinities. So that will be trying to add a second electron to a singly negative anion. So for example, here we have sulfur has a second electron affinity. You notice that the second electron affinities are actually positive, highly positive for many of them, which would suggest that you should never get a second electron falling into these atoms. But indeed, we do get a second electron falling into oxygen or sulfur. And so you can think about why that would be the case, or Google it rather. You might not get any insights by just thinking about it. But that's outside of our purview on this video. So we leave it. Now we're at orange light with explaining these trends. Let's look at some questions and see if you feel confident answering them. Here's a paper 2 question. It says, explain why chlorine has a more exothermic electron affinity than sodium. Pause the video, think about what sentences you might write in response to this question. In 2 seconds, I will show you a clue, 1 and a 2 and a clue. In 2 seconds, I'll reveal my answer, 1, 2, and there's my answer. So there's how I would answer it. I'm not going to read through it because I've already explained all of that. So if you want, pause the video, read through it, and maybe you can take notes on it. Okay, here I see explain why sodium has a more exothermic electron affinity than potassium. Again, pause the video, think how you would explain this one. In a few seconds, I will show you a clue, 1 and a 2, and a clue. In 2 seconds, I reveal the answer, 1, 2, and the answer. Will I read through this one? Okay, I'll read through it very quickly. So relative to potassium we can see sodium is further up in the group, okay? And it has 3 shells compared with potassium's 4 shells. So because it has fewer shells, it has a smaller atomic radius. So when an electron falls into sodium, it's a bigger fall than when an electron falls into what? Into potassium. Or more formally, an electron coming in to sodium will occupy a position closer to the nucleus than an electron coming into potassium. And therefore, more energy is released, right? Because more energy is released when an electron comes into occupy a closer position. Okay, here's another one. This would be a paper 1 question. Pause the video as always and think about how you would answer this one. It asks, which of the following would have the most exothermic electron affinity? And I've circled them for you, although you should recognize your symbols by now. In 2 seconds, I show you the answer, and I'll show you a clue actually. 1 and a 2 and a clue. And then now here is the answer. The answer is C, okay? So chlorine should have the most exothermic of all of them. Why? Well, we know that generally it tends to get what? More exothermic across a group, right? And also what? More exothermic across a period and less exothermic down a group. So the overall trend looks something like that, right? So if that's the overall trend, we should expect whichever one is closest to that edge would have that most highly exothermic electron affinity, and that is therefore what? Chlorine. So now we have a green light with our second objective to be able to identify and explain the trends. Let's look at our final objective, which is to be able to differentiate between electron affinity and ionization energy. We've already sort of done this, but we'll do it with a bit more rigor here. So I have a stray mark there. We're going to differentiate between them based on the definition, using a picture, the analogy, the equation, the value, and the trend. Let's begin with these first two. We had given this picture here for the ionization energy, in this case of lithium, right? We said that if you put in a certain amount of energy, you can liberate an electron and form here a cation, right? And we defined the relevant definition there, or we gave the relevant definition. We can also define the first ionization energy, which is the minimum energy to remove the most loosely held electron from a neutral atom, as opposed to just ionization energy, which is for any electron. For electron affinity, what do we have? Instead of putting in energy to liberate an electron, we're gaining energy by dropping in an electron. So we're dropping in an electron into this neutral atom here. We liberate a certain amount of energy. And this was the analogy we gave of a spaceship returning to the gravitational pull of our planet. And as it does that, it tends to heat up and release light. And that heat and light being released is equivalent to the electron affinity. And the definition here is the energy change when an electron is added to a gaseous atom or ion. We can also define the first EA, which would be when an electron is added to a neutral gaseous atom. Okay, so it can't be an ion. In this case here, what we have drawn is indeed the first EA, the first electron affinity for lithium. Okay, what are the equations? So here we have a neutral gaseous atom losing an electron to form a cation, and the ionization energy is that value there. For the electron affinity, we gain an electron to form an anion, a negatively charged ion, and that is the electron affinity value there. Generally speaking, these values will be what? Will be positive, because it usually requires energy to pull off an electron from an atom, because you have to overcome the electrostatic pull of the protons in the nucleus, and therefore it's endothermic, right? It requires energy. This case is exothermic, or a negative enthalpy change, right? Because energy is released, so energy leaves the system when the electron falls into the atom. Okay? And the trend looks kind of the same for both of them, even though that's a negative value and that's a positive value. Generally speaking, this gets more endothermic as we go across and less endothermic down a group. Similarly, that gets more exothermic across and less exothermic down a group. Okay? If we look at the whole trend here for the whole periodic table, or most of the periodic table, here we can notice that, generally speaking, the areas in which the electron affinity here is highly exothermic, for example, fluorine, also tend to have a high ionization energy, so highly endothermic ionization energy, which kind of makes sense, right? Because if the electron falls a large distance, therefore releases lots of energy when it falls into the nucleus, or when it falls into orbit, you should expect that pulling off that electron would take lots of energy, right? So lots of energy in, lots of energy out. We can give two important principles here based on these pictures. The first is that highly reactive nonmetals usually have highly exothermic electron affinities. What are the highly reactive nonmetals? Things like what? Fluorine, chlorine, oxygen, right? Generally, those have highly exothermic electron affinities, which you can kind of think of by thinking of electrons as balls thrown onto the surface. If you throw balls onto that surface, the places where there's going to be the most energy released, you can think of it as the loudest sound being made, would be the deepest holes, right? So the most exothermic. So generally, the balls will make a loud sound when they fall into something like fluorine or chlorine, right? So that suggests that is the highly exothermic electron affinity. But also, the balls will tend to want to go towards the deep holes. So the highly exothermic electron affinity is kind of pulling them in that direction. Right? If you throw the balls on here, where are they more likely to end up? In the deep holes. Right? So generally nature is trying to reduce energy. Things generally go down an energy gradient as opposed to up an energy gradient. So it is the effect of the highly exothermic electron affinity that leads to the pulling force of those nuclei there, or those elements. But remember, electron affinity refers to the actual energy change. Okay? And in terms of the trend for the first ionization energies, we have this fact that highly reactive metals generally have low ionization energies. Remember that for metals, how do metals react? They react by losing electrons. And generally speaking, if it's easy for you to lose your electrons, the energy required to liberate the electrons is low, then you're going to be highly reactive. In that case, the nonmetals react by gaining electrons. And therefore, when it's highly exothermic for them to gain electrons, when the electrons are going to basically put out a lot of energy, release a lot of energy when they fall into those atoms, then those atoms will be attractive to the electrons. Here we're pulling off the electrons from the atoms, and so if it's easy to pull off electrons from an atom, those atoms will be highly reactive. Okay? I realize I'm biting my tongue a little bit, but hopefully this makes some kind of sense. We can think of here an analogy of basically the height of each bar, or the mass of each bar, is basically how hard it is to pull off an electron. So for something like fluorine, it's going to be really hard to pull off an electron from fluorine, whereas for francium, it's trivial, or almost zero energy is required to liberate that electron. Therefore, francium and folks will tend to be highly reactive because they would lose their electrons very easily. Okay, I think now we're at orange light with this. We can differentiate between electron affinity and ionization energy. Let's try a couple of questions and then we will wrap up this fairly long video. Here is the first question for you. The table below compares and contrasts EA and IE Which of the items is what? Incorrect. As always, pause the video, think of how you would answer this, and in 2 seconds I will show you a clue, 1 and a 2 and a clue, and then the other clue I'll show you in 2 seconds, 1, 2 and a clue. Okay, if you want to again pause the video, think about it. Here's our answer. Our answer is C. So C is the only incorrect one. All the others are correct. Let's look at them very briefly. The IE we know relates to electron removal, right? Here we're removing an electron from fluorine to form a fluorine cation. And this relates to electron addition. So we're adding an electron to fluorine to form a fluorine anion. And the relevant equations, you can see them there, just replace the X with fluorine. Now this one is swapped, right? So that's why C is wrong. So ionization energy is usually endothermic. It requires energy to liberate electrons, whereas this is exothermic. That is, energy is given out when you drop an electron in. And these last statements are also correct about fluorine. So fluorine has the most exothermic electron affinity, as you can see there, right? So the most energy is released when an electron falls into fluorine, whereas on this end, fluorine has one of the highest ionization energy. So it's really hard to pull off the electron, which hopefully makes sense to you, that when you drop an electron in, it should be, and lots of energy is released, then it should be hard to pull out that electron. Here is, I think, the last question. A highly reactive metal would be expected to have a, pause the video, read through the options. In 2 seconds, I show you a clue, 1 and a 2 and a clue. In 2 seconds, I will reveal another clue, actually, 1, 2 and a clue. Finally, I reveal the answer in 2 seconds. There's your answer. That was in 2 seconds. So let's walk through them. A highly reactive metal would be expected to have a highly exothermic first EA. No, highly exothermic first EAs are for what? Highly reactive non-metals like fluorine and friends there. High electronegativity? No, we haven't talked about that, but generally speaking, electronegativity is high around fluorine. A high first ionization energy? No, you can see the first ionization energy is high for the reactive nonmetals. So it must be a low first ionization energy for these guys here. And that indicates the fact that it's easy to pull off electrons from them. And therefore, they tend to just throw those electrons all about, making them reactive. Okay, I think now we are done with this fairly dicey topic of electron affinity. And I'll put some quizzes on the website if you want to go check that out. For now, we call it a day, and I wish you good luck and happy practicing. Bye-bye.